Okay, big picture. Next few days are induction. So we're going to do induction today, induction tomorrow with a little bit of review. This is called proving things by using math induction. This is called weak induction. It's hard enough as it is. We're not doing strong induction. It would take like a week in a college class to do that. Okay, so this is proof by induction. This is weak induction. All right, anyway, uh, if I wanted to prove that a little formula worked, and I just wanted to simply like show somebody it worked, I would do a simple example like, hey, you know that little formula that we use to add up the numbers from 1 to 100? And then it went to like 99 and then 100. And then, you remember how we made a formula for that? In case you've forgotten, it starts this way. See if you can finish that formula. This is the formula that adds up all the numbers from 1 to, well, anything. I'll give you a hint. It's the first number plus the last number, and hopefully you'll remember there's a special formula just for that. This is like formula inception. It's a formula inside of another formula. This is a sub n, but a sub n is equal to a plus n minus 1 times d. In case you forgot, raise your hand if you remembered that. I want to see how many kids actually had that in their brain. Okay, that's the formula we use. Now let's say I wanted to prove it actually worked. If I said to a kid, let me show you it works. If I did 1 plus 2 plus 3 plus 4, that would be the little series. I'm just going to add up the first 4 numbers because I can check so quick and easy if it worked. You know what I mean? Well, what does this actually add up to? Add them up in your head. What does that add up to? It adds up to 10. So then this whole right side better add up to 10. And I'm going to just show the person, hey, it's working for 4. Would you agree that n equals 4 in this scenario? Okay. Then this would be 4 over 2 times 4 plus 4 plus, oh wait, I'm doing it wrong. 1. A is 1. Start with 1. Plus n minus 1, which is 4 minus 1, times d, which was 1, is going up 1 each time, right? And does that actually equal each other? Yeah. 10 equals 2 times, that's just 3, plus 1 is 5. And look at that. I'm not done until I say 10 equals 10. Some rules of proofs. You're not done with the proof until it reads exactly the same on the left and the right hand side. And then you have to have everything above each other has to be identically equal. Like that has to equal this, which has to equal that. Okay, so then what is a proof by induction? A proof by induction is not this. Would you agree that this didn't really prove that this formula always works? It just proved it worked for this one case. If I add up the first 4 numbers, it works. Now, most of us are like fine with that. That's good enough proof for us. But if we want actual real proof, you can't just prove it works for one case. You have to prove it works for everything. So the proof by induction has a ladder motif. And here's what I like to think of it as. Let's say that you were going to have grandma says, no, I can climb all the way up that ladder. And you're like skeptical. Grandma, I'm not sure you're going to be able to make it up that ladder. Would you agree that it would help if she could just take the first step? Like she'd actually step up on that and like steady yourself. You'd be like, okay, that's like the minimum you'd have to do, right? Is be able to do it once. That's like sticking in a number into the formula, like trying it once. N equals 1. Or we just proved n equals 4 worked. Then, if you could put Granny on any step, pick any step you want, and you just like carry her over there and place her on that step, and she's always able to take the next step. It's easy for her to take the next step. Then, if you could put her anywhere and she could always take one more step and it would always work, then you might trust that she'd be able to get up the ladder. Okay, so to prove that this works for every single term, you don't want to try to prove every single rung of the ladder. Do you get what I mean? That would take forever. So what you do is you prove it works for one of them, then you prove it works for any one that you pick, like, I don't know, maybe that one. And then if it works for that one and the one after it, as long as this is a randomly chosen spot, then you've proven that it'll work for everything. So what is the random step called? It's setting n not equal to a number like 4. That wouldn't be any term. It's setting n equal to k. K is a randomly chosen term. And then, this is the biggest stretch, what would the one after that be? K plus 1. All right, so what you're going to find when this is over with is, I think this will make sense to you. We're doing like f of x. Okay, and if we're going to prove that this works, we do f of 1. That's sticking in a 1. It's super simple, and you prove that it works if you stick in 1. Then you stick in f of n. Nope, sorry. F of k. Our function already has an n in it. So we pick a random term k, and then we make it work for that. And then last but not least, we take the next step up, which is right there, which is k plus 1. Those are your 3 steps to proving something. You prove it works for 1, or it doesn't have to be 1. It can be any simple single-digit number. Then you prove it works for the random case k, and then you prove it works for the one after that, k plus 1. All right, so this is going to get pretty intense algebra-wise, and I don't feel bad telling you that this is, the stuff at the end of this is hard enough that I will expect that not everybody will get this. It's okay. This is our last thing we're learning this semester, and if you can get about through steps 1, 2, and setting up the 3rd step, that's as far as we need you to get in honors pre-calc. A lot of classes don't even do this. A lot of pre-calc classes don't even try this. Okay, so if you can get to just set up the 3rd step, then it'll be okay. I won't need you to solve it all the way. If you can, and you can prove that you can solve the 3rd step, you'll see how hard that is in a second, then that's worthy of extra credit. So what are you expected to do? You're expected to be able to get to this right here. And let me show you how you can get to that right there. First of all, here is my thing that's supposedly true. Would you please examine the left-hand side of this? Do you get that appears to be a series? What is its starting number? 2. And it seems to be going up until, well, do we know when it stops? No. So if n equals 1, this whole thing, this is a term generator, and it's 2 times 1 is just 2. The whole left side is just a 2. There's only one term. That's kind of a weird case. What if we stuck in n equals 2? Let's say we have a 2 here. Do you get that then you'd have a 2 as your first term, and that's your last term, and your last term would be 2 times 2 is 4. That means you only go to here. All right, I'd like you to check it for n equals 3. Because n equals 1 doesn't make much sense. I want you to stick in 3. Just check and see if for 3 terms, this little formula here actually adds them up properly. Stick in n equals 3 and see if it works. What that's saying is the sum of the first 3 terms, and that little formula should generate it for you. So what was our last term? 2 times n, which is 2 times 3, which is 6. 6 is the last term. That's basically saying add these all up. So the left side is just 2 plus 4 plus 6, and it stops there. How do I know it stops there? Because n is 3. The last term is this. This is the last term. 2 times 3 is 6, so it ends with a 6. I know some of you are like, but there's already a 6 there. That's just saying that it starts at 2 and keeps going until it ends, and it ends wherever this thing says. So 2 plus 4 plus 6 equals 3 times 3 plus 1 is 4. And look at that, it actually worked. Did I prove it works for everything? No. I just proved that it worked for n equals 3. Do you remember me saying it isn't always n equals 1? I just proved it for n equals 3 because it made more sense to me than n equals 1. I'm going to go back now and just prove that this works for n equals 1. See if you understand what I'm doing. If I want to prove it works for n equals 1, and I'm going to put a 1 right here, I'm going to realize that my term list starts with a 2 and its last term, its biggest term, is 2. So this is just 2. And then the other side is if it's a 1, 1 and a 1, and does it appear to work? 2 does equal 2, doesn't it? So there we go. There, I proved it twice. I didn't have to, but just to kind of give you the idea of what's going on here. I stuck in a number and made it work. And step 1 is to prove it works for something simple like n equals 1. Don't have to be slavishly following that. It could be n equals 3. You could try n equals 5. Something that works nice. Yes?
Well, I thought the last term of the term on the left was
It is. So if you want to make n equal 1, what is the biggest term? N2 is the first term, and it's the biggest term, so there's only one term. So what if n equaled like 6? 6 and 2 is 12. So this thing keeps going until 12. 2, 4, 6, and it's not like you just skip something. You'd have 2, 4, 6, 8, 10, and 12. All right, so this is a big list on the left, and it's showing you that you can add them all up. All right, that's the first step. Then this step is something that's kind of weird. Step 2 is prove that it works with n equals any randomly chosen step on the ladder, which we call k. Do you get all they did is put the original formula and stuck in a k? Do you get that? This is identical, except they stuck in that n was k. If you can't handle that, then you're not even trying, because that's just sticking in a k. Now, that's the proof statement that we have to prove. We don't know if it's true. I know that's weird, but we don't know if that's true. We're saying we want to prove if this is true. So I'm going to even put a little question mark. I know some teachers do that above the equals and say, I want to know if that's true. Okay. Done. I'm done with that step. I put in a 2. Sorry, I put in a k. Sorry. Now I'm going to go to step 3. And this is the one where all the nasty algebra happens to actually prove that this thing works. N equaled k was just a swap. This just turned into that. But n equals k plus 1, you're really going to have to know what you're doing. Do you get we have the original up to here? It's the same exact thing up to there. But do you get they added one more term to the sequence, which would have been 2n, except they substituted n for k plus 1? They added one more term to the sequence here. Okay? And on the other side, can you see what they did? If you see it, can you see what they did? What did they do? Yes? Yeah, wherever we had an n before, in the original formula, see, that's where we had an n, and now we had a k, and now we put a k plus 1. We had an n, became a k, now it's a k plus 1. So some of you, and I would get why you'd think this, some of you would think, why didn't you just change this k into a k plus 1? It would have been super simple, Mr. Server. You could have just said, take this, and wherever you see it put a k, you put a k plus 1. Well, I could do that. I could. If I changed this right here to a k plus 1, wouldn't it be true that the term right in front of this would have been 2 times k? So if you want to think of it that way, you can. We're just swapping everything that was a k and originally was an n with a k plus 1. All right, so that brings us to this crazy looking thing that I have to prove is actually algebraically true. And I know some of you, with a lot of time, could be able to manipulate one side of this until it looks like the other. Here's what you'd do. You'd take this side and you do a whole bunch of little tricks to it until it looks identical to that side, which would include things like factoring and substitution and breaking things up into little parts. And this, without my help, I bet you there's only one, maybe two people in the whole room that could figure this out. On the test, would I expect everybody to know this? No. On the test, if you could do this, could you get some extra credit? Yes. All right, so let's see if you can hang with this explanation. First off, this is the big wonder stroke. That can be pulled out and replaced with what? Only 3 people have ever raised their hand today to answer this one. And one of them was wrong. Come on. Think you got it? What do you think? Maybe. You cannot replace it with anything related to n. But you actually were kind of close. If I put anything with an n in there, I'm introducing a new variable. That's not good. What do you think? Why? I'm not saying you're wrong. It might actually work, but you're actually really close, but I don't think you've quite got it. Because maybe your answer is equivalent to mine, and you can look it up later and see if it is. He's got an idea. Look at the board, everybody. He's right. It's k times k plus 1. Because look, it says right here that that equals that. So that means wherever I see the one, I can put the other. So I can replace this with k times k plus 1. And somebody said k squared, and that would be k times k. Okay, so that was kind of close. All right. So now I've replaced this whole thing with that. Do you get that that makes sense? Because it says that that's equal to that. This whole thing is equal to that. So wherever they are, I should be able to swap them. Then I'm just going to bring this down. Plus 2 times k plus 1 equals k plus 1 times k plus 1 plus 1. I know some of you are tempted to just like put those together and say plus 2. Can't do that. Because in a proof, you can only manipulate one side. You can't manipulate both sides until they're equal to each other. That's breaking one of the rules of proofs. If you're going to do a proof, you can only mess with one side or the other. And you keep on messing with that one side until it equals the side you haven't touched. So I'm going to leave the right-hand side alone. I'm going to quit copying it down. I'm just going to put ditto marks the whole rest of the way. Okay? And again, I get it. Some of you won't get this. But I'd like you to think of it as a challenge. Who thinks they have something I could do to that that would make it look like the other side? I want to just give a minute for people to try this. Try something. You think you might have it, try it. Write it out. See if it's working. We want the left side to equal the right side. I'll write this down. Really. It would really, really help. It's so rare to have opportunities that you know ahead of time of what you could do to study for extra credit on a test. Thought? I have two people with thoughts now. Since he had his hand up first, I'm going to give him first shot at it.
This is the same as if you factor k plus 1 to k plus 2.
Are you saying, what are you saying I should do to the left side?
Factor out the k plus 1.
Because if you can factor it, you should. He saw that there was a k plus 1 in both of those. Is that what you got? Other people that had your hand up were thinking? Because you're right. All right. Yeah, factor out the k plus 1. There's one in here and there's one in here. Do you remember factor by grouping? It's already pre-grouped. And so then what's left is k plus 2. And you might be saying, but Mr. Server, that's not identical to this. Oh, it's really close. What's the only difference? The 2 on the other side, what's it represented as over there? A 1 plus 1. Can't I replace a 2 with a 1 plus 1? You're not used to doing that. You're used to always making them simpler. Can you instead make them more complicated? As long as you're substituting in something that's equal, you can do that. And I just replaced a 2 with a 1 plus 1, and it's totally okay. And now I've made the left side equal the right side, and I've got some extra credit on my test. Because I was able to finish the algebra to prove algebraically that not only does k work, but k plus 1 works, and that proves that k works. It's complicated, but bottom line, you had n equals 1, n equals k plus 1. The n equals 1, anybody can do that. Stick a number in. N equals k, anybody can do that. You swap the n out for the k, and you're saying, let n be a random term, k. And then, the hard part is putting in the k plus 1. Yes?
How come you do the k plus 1 plus 1?
I get what you're saying. Do you get that I had already made changes to the left-hand side? So I can't change both the left-hand side and the right-hand side. Otherwise, I'm breaking one of the rules of proofs, is that you can only manipulate one side or the other. I get what you're saying. And some teachers actually allow that because they, like, that's too complicated to put in there. But I want you to be ready for that when you hit calculus. So you can only mess with one side or the other. You can't tweak both sides until they're equal. That's breaking one of the rules. Actually, in really high level math, you can, but then next to each time you do that, you have to put a justification of why it's okay to change the one side and not the other. So in some complicated situations, you actually can change both sides, but it's even more complicated because you have to put reasons on the side. So what you'll be expected here at the high school, just to know that you aren't done until this side exactly equals that side exactly. And lastly, you only can mess with one side or the other. And since I was making changes to the left side, I couldn't tweak that and make it 1 plus 1 equals 2. But anytime you see something that's that simple, it also can be done kind of backwards. You can take something that's simple like 2 and break it up into 2 parts. All right. There's one here that would make everybody's eyes cross. It's so complicated. But I don't want to do that one yet. Maybe at the end of the hour. Okay. First, let's go over these steps before we ask your question, okay? Step 1, prove it for n equals 1 or first available n. What that means is, what if n isn't in your domain? What if you don't want to start with n equals 1? You can start with any number you want. You don't have to start with 1. Okay? Remember that one time I started with 4? You can do that. Okay, next. Assume that that's true for n equals k. This is a better way to say it than what I was saying. This is the more official math way to say it. I was saying you get to pick any starting spot. And instead of n, I'm going to call that k. Another way to say it is I'm going to assume that this is true for n equals k. And then the last step is I have to change it to k plus 1 because that'll be the whatever the next step is. All right, so here's one. This is not a super complicated one. In fact, I already alluded to it earlier in the hour. See if you can do it yourself. Hint. First step, prove n equals 1. Second step, prove, actually this is an assumption. I shouldn't even say prove, I should say assume. And lastly, I get most people can't finish the last step. But if you're one of my extra smart kids who are knocking the ball out of the park on your tests, you could do it. I'm going to pause for a second and give this a try. Okay, so let me show you how far you have to be able to go. N equals 1. Again, do you have to use 1? No. You could try n equals 5 if you're more comfortable with that. I'm going to choose 1 because I understand what this means. This does not mean 1 plus 2 plus 3 plus 1. It means my last term is 1. Well, then that means it starts at 1 and it ends at 1, and this whole thing is just 1. Then I'm going to stick in n equals 1 over here. It's as simple as it seems. 1, 1 plus 1 over 2, and that means 1 equals 1. Yay, it's true. So I'm proving something. I proved it works for one term. Next step. Assume that n equals k. 1 plus 2 plus 3 plus ... plus k. K. That is easy. You just stick in a k. Any questions on that one? That's saying instead of sticking in like a 1, I'm going to stick in a variable like k. All right, now I have to prove that the k plus 1 thing works. Now here's, I shouldn't erase that. I should leave that. Yes. I'm going to now take this equation right here, and I'm going to add a term. Remember, that's a big list of terms. 1 and 2 and 3 and ... and k. I'm not going to replace it with k plus 1. I'm going to add one more term, which will be k plus 1. That, I think, might be the trickiest part right there. Because these, you just replace the k with a k plus 1. So that becomes a k plus 1. That becomes a k plus 1. And then it says plus 1. All over 2. There. Set up. If you can go that far, you've got the level that we need. It's only like an R2 level question to set that up. That's pretty easy. Now to actually solve it, I'll finish it off in a second here. Yes? It doesn't have to be. Although, actually, it probably should be. You'll see that the other teacher made the same mistake on a future slide here, but you're right. When I replace the k, it's like an empty parenthesis around the k. I should really be dropping in a k plus 1. You are right. Good call. I should have a k plus 1. Yep, I should have a parenthesis around the k plus 1. This one, it's a little more, I suppose I should have one there too. Although since it's an adding, it really won't matter, where the other one is a multiplying, and so it technically does matter. Okay, if you caught what one student, actually, and then there were the other 3 that had their hands up, noticed, that is the same thing as that. So you can replace the one with the other. Plus that. And I'm not going to keep writing the right side. I'm just going to bring down with dittos the right side, and I'll never touch the right side. And then if you can factor it, you should. You remember that deal? K plus 1 comes out to the front. What do I have left? This is a little strange, but that's what I'd have left. And at this point, it might be tempting to be like, that doesn't look at all like what it's supposed to look like. But it actually is really close. Do you get how I got that? Once I pull a k plus 1 out, technically replacing it with a 1. Do you see how I get this? It's important to be able to make that leap. I just factored out a k plus 1. Okay, now to finish it off, would you agree that a 2 over 2 is equal to a 1? So that's a substitution I can make, isn't it? Okay. Then would you agree these can now be added together? And it'll become k plus 2 over 2. And this one's still k plus 1. Are you with me there? And then remember, my goal is to make it look like this. What's the only thing that's different now? Well, it's all one fraction over here, one big fraction. Well, let me multiply these together then. Common denominator. Don't even need a common denominator to multiply. So I'm just going to multiply across the top. And there's only one more step. Would you agree that 2 could be replaced with a 1 plus 1? And that is identical to what we had right here. And that's the 12-minute warning. Okay. That was kind of intense. Would you have to do that stuff at the end? Nope. Would you have to be able to get to here and write this statement out? Yep. That's what you have to be able to get to. From there, it's not that bad if you remember to replace this with something previous. And then it's always going to come down to if you can factor it, you should. Really, with those 2 hints, if you're good at algebra, you can do that and you can get the extra credit. All right, so I'm really tempted to show you this one. I think I'm going to in speed version. Okay. First, I have to prove it's true for n equals 1. So I stick in a 1. Does that mean I need all of this plus a 1? No, it's just 1 is my last term, so 1 squared is 1. There's only a 1 on that whole side. 1 equals. And then 1, I'm just putting in a 1 everywhere I see an n. 1 plus 1 plus 1. 2 times 1 plus 1, all divided by 6. That part is just 6. 1 equals 6 over 6. 1 equals 1. Yay, I proved it for n equals 1. Anybody could do that. That's easy. Next, I'm going to put in n equals k. All that is the same exact formula, except you put a k in. It is so easy. Oops, that's k. Whew. Nastiness. All right, then, actually I already started my, yep, I made a mistake, sorry. I should be replacing it with just k right now. Wherever I see n, I should be putting a k. I was doing a k plus 1 in one of my spots. There, all I did is replace, wherever I saw an n, I put in a k. Then my last step is that proof. Where I put in, let n equal k plus 1. 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared. I leave that there. And then I also include a k plus 1 squared. And then I replace all my k's with k plus 1s. So k, 2 parentheses k plus 1 divided by 6. Whew! That's how far you'd be expected to go. Now I'm going to solve it for the people who like heavy-duty proofs. That part. was defined earlier. That part was defined right here. So I'm going to replace the green circles. And then it's plus this. And then, thankfully, this is the moment where I can just say ditto here. I can carry that down forever. Now it's just all about manipulating this left side until I get it to look like the right side. All right, so my first thought is, it'd be nice if I had a common denominator, because this one, it's this whole thing over 6. And on mine, I don't have a common denominator. So I'm going to put this as a 6 over 6. Now it has a common denominator. So now it can be put together. So I'm going to go k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared all over 6. Now, would you agree that right this second, I already have the divided by 6 that I need, and I already have a k plus 1 that I need. But what haven't I done that I mentioned I would always need to do? It's my favorite strategy of them all. If you can factor it, you should. Do you get out as a k plus 1 in both parts? Then that k plus 1 can be factored out. And then what's left if I do that? That, and the 6 times k plus 1, because this was squared right here. All over 6. Whew. Now, I've already got the k plus 1 I need. Yay. Already got the 6 I need. Yay. Now I just have to get this part right here to look like this part right here. I'm going to take this part right here and make it 2k squared plus k, and plus 6k plus 6. And that's multiplying that 6 out in both parts. And I'm just going to bring this straight down. This all needs to be in parentheses, and it all needs to be over 6. All right. Now, It's working. It's working. And then this part here needs to become, I got the k plus 1 over 6 separated. That needs to become that. So now, would you agree that k plus 2 could be changed into k plus 1 plus 1? K plus 1 is the same as k plus 2, isn't it? And that's that. And then the last thing I have to do is make the other part 2 times quantity k plus 1 plus 1. This, so I'm going to rewrite this. Only this is different than that. So I got to be able to break that up into 2 times k plus 1 plus 1. And guess what? That is equal to that. Multiply it out and see. 2k plus 2 plus 1 is 2k plus 3. Okay. You see why I wanted to finish that one and do it right? That was a really hard question. It was like the ultimate challenge. I just needed to finish it. Could I expect you to do that on a test? No. If you could pull it off, should you get extra credit? Yes. All right. There's only one problem on the homework. Actually, there's two. You only do the first one. The second one, it's really not like what we just did. Just do one proof. It's the first one. It's not super hard. It's your only homework for tonight. And hint, I need to get one more thing in the gradebook at least before the end. This might be it. And it's super simple, so I wouldn't even feel bad if the kid didn't do it. There's one problem. The first problem of your homework. Do it. I'm not promising. I never promise, but it's very likely I will grade that tomorrow. Okay, that's all I got for you for today.